Okay. So I'm using different software. That's why just कोई एक check कर सकता है कि तुम्हारे पे दिख रहा है? YouTube पे दिख रहा है? Okay. Okay. So good morning for lecture number 13. So I hope you enjoyed the exam, which was very easy, but so people got. So I think I sent. Anybody received the? No. So maybe some glitch in the program, right? So anyway, we will check again. Or anyway, you will be getting copies today. So जब इतना इंतजार किया है तो फिर now you can get the right. Anyway, so today actually I am going to start with. Actually, I will call it as a recall. So each of you know definite integral, right? A to b f of x dx, right? And it is nothing but area under a curve kind of thing, right? So that idea is very important. It's known as Riemann integration, right? Riemann sum. Okay. So we'll briefly recall that stuff, and then after that we will start functions of two variables. Okay. So now, till now you are looking at function of single variable. If f is a function from real line to real line, right? What happens if f is a function from r square to r, or r cube to r, or r raised to power n? So n input, one output. Okay, that kind of function. Or in case of two variables, two input, one output. So when we talk about these kind of functions, the first thing you would like to know: domain, range, and how do you plot them, right? Those are three basic things. And after that, you talk about your popular limit, continuity, and differentiability, right? And limit continuity, when I say in terms of epsilon delta, right? That will come automatically, right? Now, one thing you will notice that in case of single valued function, right, from real line to real line, our neighborhood was kind of a interval, right? From interval you go to another interval, right? So when x approaches towards a in an interval, right, either from left hand side or right hand side, actually image is in the neighborhood of some fixed number L, right, if the limit exists. Here, because on the left hand side you have r square, say for example in n is equal to 2, when we are looking at a plane. So now function is defined from plane to real line. Now the neighborhood becomes from interval to a circle. Okay, and so now a point approaches towards a comma b. I mean the center point of the circle is a comma b, right? And you approach, so any x comma y point approaches towards a comma b from any side along x axis, along y axis, or any other curve, right? So that is a key difference. And then rest of it, all epsilon delta things remain same, except one thing. There the idea of distance was, so distance between 2 point x comma y was mod of x minus y. Here distance is, you can vary the distance. For example, you can have Euclidean distance between the points, right? So the limit will change accordingly, right? So the definition will change accordingly. So idea is very simple, okay? Then similarly you can talk about continuity, and then differentiability has a lot of interesting facts. I don't think I will be able to do anything about the differentiability today, but so let us start. Okay, so suppose f of x is a continuous function on a closed interval a comma b, and suppose small m is the minimum of f of x, a less than or equal to x less than or equal to b, and capital M is maximum of f of x, a less than equal to x less than equal to b. So actually I am going to describe your definite integral. You know already these things, but you know, just for the sake of again recalling it, because the idea is really very, very important. I'm just taking some function, right? Okay. So suppose this point is, so what I do actually, now I divide this interval a comma b between subintervals xi minus 1 and xi, right? Where I, so 1 less than equal to I less than equal to n, okay? With x0 is equal to a, first endpoint, and xn is equal to b, okay? So we can say that here we can say that a is equal to x0 is less than x1 less than x2. So anyway, a is equal to x0 less than x1 less than dot 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 less than xn is equal to b, okay? So we have a function here f of x continuous on a closed interval a b. So obviously there will be minimum and maximum, right, for that function. I call it small m and capital M. Now I can divide. So suppose this is your first point, and I'll just somewhere here say this is your x0 a, and say this is equal to xn. So there are two endpoints. I mean, forget about this portion, right? I'm just saying the function is from here to here, right? So this is the first and this is the second. Now I divide the whole interval into small pieces. So why I am doing this? I want to compute this area under this curve, okay, from a to b. And how do we do that? So one nice way is, somehow I take an arbitrary interval here, right, subinterval, I mean, and then compute the width and compute the height, right? Then so we'll have the area of a small strip, right? Then you can add all the strips, you get the whole area, right? Now one thing is there, in each strip there will be minima, maxima, or some point, right, I can take. So accordingly the height you may vary, right? So for smaller intervals, like if you divide n to be 15 intervals, if you divide, somebody will say that, okay, I want to divide the whole interval a to b in 15 subintervals. Somebody say that I want to divide into 100 subintervals. Somebody will say that I want to divide into 1000 subintervals. Which result is better? 1000, right? Jitna chota karte jaoge utna acha hoga, right? That's the key point, okay? So now let us see. So suppose this is x1, somewhere here suppose this is xn minus 1, right? Okay, now I take this is say xi minus 1, this is xi, I call this point as xi, chi I, okay, chi I, okay. Now you see there are two things, P, Q, S, and suppose this point is M, right? So here actually the curve is like this, so a strip looks like this, right? So if I want to compute the area, you see that this point will give you the height, right? This is the length here, right? If you want to compute the area of this strip, this into f of this value xi or xi I, f of xi I, which will be the height, which will give you the area. But this will be approximate depending upon what is the location, right there. Because sometime this rectangle will go above the curve, sometime it will be below the curve, right? I'm just giving one example, but in general what will happen, right? So sometime it is more area, sometime it is less area. And it all depends, because what is the width, how many subintervals you take. But this will be very good if these two subinterval points are very, very close. Okay, essentially it will give you the exact area when the subintervals goes towards infinity, the number of subintervals goes towards infinity, when n tends towards infinity. Then actually you get the very good approximation. Okay, that is the key thing. There are many animations also available, but I will show you that later on. So your xi is a point, xi, I should say xi is a point in xi minus 1 and xi. Okay. Now, in fact, each subinterval will have minimum or maxima, right, of the function, right? So I say that here mi is minimum of fx between xi minus 1 x less than or equal to xi. Okay, here again 1 is less than or equal to I less than or equal to n. Same thing, capital Mi is a maximum. Okay, between this of fx. Okay, so now everything is ready. Now if I want to compute the area, what I should do? So this length is what? We call it delta of xi, right? Which is difference, right, between the points, right? This will give you this length, and typical area will be times f of xi, right? And then you sum from I is equal to 1 to n, right? Then it will give you all strips, area of all strips, right? So we have, so actually there are, so when I am summing, if I take small mi to be the minimum between this subinterval, so I can form a sum what is known as lower sum, right? Lower sum, right? Similarly, if I take capital Mi, so then we will get upper sum. So there are two kind of sum you are getting for each subinterval thing, right? So these lower sum and upper sum will converge towards the same sum when n approaches towards infinity, right? That is the key idea, right? So we can define what is known as lower sum summation I is equal to 1 to n mi. What is small mi into delta xi? Mi is the point, right? Minima times delta xi, right? So that will give you what? Some sum, right? I mean the area of that strip, right? I call it, so it is the actual area lower bounded by this thing actually, right? Similarly the upper sum. Okay, and I can define Sn of f summation I is equal to 1 to n f of xi. So I can define three kind of sums. Xi is a point between xi and xi minus 1, right? And if I compute f of xi, that will be the height of the strip times breadth, right? So overall is the area. And in the same interval, we can take mi and small mi and capital Mi. You will have two other areas. What is the relationship between all the three sums? So obviously, this will lie between these two, right? Right? Because the height will vary, minima and maxima. Minima will give you lower sum, maxima will give you upper sum, and if xi is an other point, arbitrary point between those two, then you will get midpoint actually. So you will get actual, right? It's a typical scenario. So now the relationship is this, that Right. If we take n approaches towards infinity, so in that case, maxima of delta xi goes towards 0, and actually in that case, all these three will become same. So we should say that limit n tends towards infinity, lower sum is same thing as n tends towards infinity, a typical sum same thing as limit n tends towards infinity, and we denote it by a to b f of x dx. This is how definite integral is defined, right? Got the idea? It's a very simple idea. I think you know about it also already. ये तो पढ़ा होगा ना? So this idea is very important actually. If you want to find area under the curve, because this is a single variable case, so you just take the small strip, compute the height at a typical point, and the breadth, right? That multiplication will give you the area of the strip, right? And actually, later on, I am going to generalize it to two variable case. Okay, so then it will not be a simple curve, but actually a surface, and then we can do double integral. Similarly, sometime I want to do a triple integral. How do you represent them? Then this idea is going to be beautiful, right? So it was just recall. There are some standard properties which I think you know, but I can mention quickly. Already 16 minutes ho gaya. First property. I am not going to prove it. I mean, on any sunny morning, you can take a cup of tea and then enjoy these things. Where? This is second one. Third one, which is sort of important. Right. And actually the one which you use quite often right, this you do quite often, right? So I think that's all. It was a 15-minute recap of definite integral. There are many other properties, but that's okay. I mean, this much is enough for you. Now, by the way, yeah, so now you can actually install Wolfram Media Player, and I have given you the link here. You see, you can see this Ramansam illustration also if you are really still want to recapture the idea, right? Click on this link, okay, and you can watch. You can vary the partition number. N is equal to 15, what will happen? N is equal to 100, what will happen? And you can see actually the whole strip how it varies, right? I cannot show it here because of certain reasons, right? It will be copyright, right? If I show it here, so you can just use it. Okay. Similarly, we have another demonstration. By the way, so if you install Wolfram Media Player, which is free, these demonstrations are available freely on the website, so you can see them. Okay. So you can install that and you watch it. It's a very useful software, Wolfram Alpha or Wolfram Media Player. You can use in on your mobile also. Okay, so now I am worrying about multivariable calculus. Okay, multivariable means, so one can say that from n input to m output. That is the most general case. वो तो यहाँ करने बैठेंगे तो फिर दिक्कत हो जाएगी. तो n input to single output, वो भी थोड़ा जरूरत नहीं है. 2 input और single output पे ही फोकस करेंगे हम, right? वैसे 3 input से and 1 output is also okay. Okay, so that is something that, so basically they have something like this. our space by the way, this is, do you know what is this space? It's a, you know, n dimensional space, right? There are n basis vectors, 1 0 0 0 0 0 1 0 0, right? Any vector in the space can be written as a linear combination of these three basis vectors, sorry, n basis vectors here, right? So I think, you know, if you take n is equal to 2, there are two basis vectors, 0 1 and 1 0. Any point can be written as a linear combination of these two basis vectors uniquely, right? So, you know, so that is a very, very important thing to know. This is a vector space. I think vector space you will study. It's a very, very powerful concept. Okay, and so vector space means, you know, if you take two vectors, add them, you are in the set. Take a vector, scale it, you are again in the set. These are the two basic properties, right? So that the whole becomes, you can play actually with the vector space. Okay, so so there are different kind of way we can define calculus. One way could be we look at functions from Rn to R, functions from R to Rn, functions from Rm to Rn. Okay, so I am only going to worry about this, and that too functions from R square to R. I am going to focus in this course only these kind of functions, right? 2 input, 1 output. Okay, so f of x comma y. I'll give you one example of 3 input 1 output as well to give you some idea, but I will not discuss any more than that. Okay, so it's a multivariable calculus. So for these kind of functions, let me give you an example first. Here is a f of x comma y is equal to square root of 9 minus x square minus y square. So first of all, if the function is given like this, I need to find domain and range, right? How do you find domain and range? Domain and range answer is given, but can anyone tell me how do you find that? It's very easy, right? So when 9 minus x square minus y square is non-negative, right? And you can solve that. That means when x square plus y square is less than or equal to 9, right? So you have the domain, right? For all those points x comma y, which is what it is given. Output, so range, how will you find? Domain is easy here, right? Any doubt about domain? Domain is easy, right? What about range? Let me write it down for you. So domain is obviously this portion. If this is x square plus y square is equal to 9, right? This whole interior point, right? That is a domain, right? D. Okay, now range is all those points z such that z is equal to square root of 9 minus x square minus y square, where x comma y belongs to domain of f. Agree? If I have to find range, I am saying range is nothing but all those z, which is this square root, such that x y belongs to domain of f, right? They are the top, which is, so condition on x comma y is x square plus y square is less than or equal to 9, right? Now, since z is a positive square root, we know that z should be non-negative, right? Also, 9 minus x square minus y square less than or equal to 9. This gives us that square root of 9 minus x square minus y square less than or equal to 3. Right. So that means we get, this is nothing but z. So basically, range of f is all those points z such that 0 is less than or equal to z is less than or equal to 3. Right. So easy. But now you can see. Now can you see there is this kind of bulb here, right, in the function, because for those points, right, there will be bulb, right, when domain is something like a circular disk, right. So that will give you this. Let us take another example. What about this? This is a 3 input 1 output function. So I leave it as an exercise for you to find the domain and range for this function, right. So you can see that domain is all those points in R cube such that y is less than z. Okay, and range is whole real number. By the way, again, as I mentioned, there are a lot of demonstrations are available for plotting. And one thing I just want to mention that when we are plotting single variable functions, so it's a graph, right? Sort of a curve in the plane. But when we plot 2 variable function, how do we plot? So I need to plot 3 points then, x, y and z, which is the output function of x comma y, right? So 3 axes will be there. So essentially you will be getting a surface. So whenever we are plotting a 2 variable function, we are getting a surface. Ab surface kaisi bhi ho sakti hai, right? It could be up and down, or somewhere a tier or something like that, right? So whenever we are plotting function, 3 variables are required. So x, y, z. X, y are input, z is the output. Okay, 2 input, 1 output. Any question about this 2 variable function? That's okay. So you can see a lot of demonstrations. So now many times if you want to understand the surfaces, I mean, we also, so one way is just plot both in other x, y, z, you plot, you get some surface, you can visualize it. Just now you saw that. But actually there is another important concept known as contour plot, which is defined by level surface. Okay, so I'll talk about level curve basically. So what is level curve for each surface? Okay, it's like a slice. So there are different, so you can say that a surface is made up of different slices. Okay, so different slices you take. If so, basically, if you want to really understand the whole function, just look at one slice of the function. I mean, a 2 variable function means just look at the one slice of the surface, and you can get some idea what is going on there, right? I'll show you that picture also. Anyway, so I should mention here what is called is level curves of a function of 2 variable fx comma y is, so curves with equation y is equal to k. K is a constant, right? So for example, draw the level curves. K I should say is 0, 1, 2, 3. K is a constant which you can vary, right? So k is equal to 0 will give you one slice. K is equal to 1 will give you another slice. K is right. So different slice will be given to you, right? You see, because what has happened, f of x comma y is z. Z is equal to f, so f of x comma y is z, right? If you vary x and y and z, so you get a whole surface. But I am saying that if you take f of x comma y as one fixed number, k, that is one slice, right? Then take another one and take another one, right? So whole thing can be built. Okay, so this is known as level curves of. This is an exercise I'll ask you to do. Find the level curves of this. For k is equal to say 0, 1, 2, 3, right? Or contour plot, whatever way you like it. Anyway, so now we are ready with limit of a function. Okay, we say that limit of a 2 variable function f of x comma y, x comma y approaches towards a comma b. This is the normal way you write, is L. If what happens? I mean, this is how you say that, right? A 2 variable function will approaches towards a point L now rather than x tends towards a, we have x comma y, a typical generic point x comma y approaches towards a fixed point a comma b, right? If this thing is happening and this value, if this limit is L, then we say that, I mean, the limit exists. But how do we define limit now? So your favorite friend epsilon delta will come into picture, right? So what you need? First, the distance, the idea of distance between x comma y and a comma b, right? The idea of distance you require, that is the first requirement. Second requirement, the distance between L and f of x comma y. So whenever x comma y is in the neighborhood of a comma b, you see, whatever I am speaking is very careful, just listen it. Whenever x comma y, the generic point x comma y is in the neighborhood of a comma b from any direction. There it was only left hand, right hand. Here from any direction, right? X axis, y axis, you know, along a straight line, along some curve. If x comma y approaches towards a comma b from any direction in the neighborhood of a comma b, which is a circular disk kind of thing, right? Then image of the function f of x comma y lies in the neighborhood of capital L. But there the neighborhood is again an interval because function is from r square to r. Okay, so on the right hand side there is a point L and epsilon neighborhood. So that means, so mod of f of x comma y minus L is less than epsilon. So how do you define the definition? If for every epsilon positive there exists delta positive such that distance between x comma y, I am just अभी distance के term में बात करते हैं, such that distance between x comma y and a comma b is less than delta. I mean, whenever, sorry, so whenever distance between x comma y and a comma b is less than delta, mod of f of x comma y minus L is less than epsilon. One great definition, right? Right? There the distance is mod, so I am using mod. Here what distance I should use, that is up to us. So by the way, a beautiful tea time problems could be, what kind of distances are possible in a plane? In r square, one distance is equivalent distance. So distance between x comma y and a comma b is what? Is square root of x minus a whole square plus y minus b whole square, right? Equivalent distance. Another distance could be Manhattan distance. सुना है नाम इसका? Maximum of mod of x minus a comma x minus b. Right, that is also a distance. So what is the property of this? So if a distance function is defined as a function from x comma y to some number, right, such that first d of x comma y is positive, greater than or equal to 0, and is equal to 0 if and only if x equal to y. Number 2, distance between x comma y, same thing is y comma x, right, that is symmetry. And third is triangle inequality is satisfied. These are if the three properties, these are the three properties that the distance function should be satisfying, right? So I can take any distance. I can take, while defining the limit of a function, I can take Manhattan distance or some other distance. So I leave as an exercise for you to find 3-4 distance at least on the plane between 2 points. In a plane between 2 points, how do we define distance? Equivalent distance, so straightforward, which I can write anyway, right? Got it? So this is how the idea of limit of a function. So let me write down the definition now. So basically, this is r square. This is a point a comma b, and this is the neighborhood of a comma b. Suppose this is a typical point x comma y, a generic point x comma y, right? And this, so now you can see that this point x comma y could be anywhere in this circular disk, right? But it is approaching towards a comma b from any direction, right? From any curve, along any curve, or along x-axis or y-axis, anyway, right? And it could be anywhere, right? If this happens, then the image of f of x comma y, so I say that this is a point L, L minus epsilon, L plus epsilon, right? Image lies somewhere here. This is on R square. This is on R, right? Got the idea? This is pictorial representation. What is happening? So x comma y approaches towards a comma b from any direction. In one dimensional case, it was only left hand limit, right hand limit. Here there are so many limits. From any direction, limit can be defined, right? So from any direction, x comma y approaches towards a comma b. So whenever this is happening, the image is always in the neighborhood of a point capital L with epsilon size on both sides, right? Any question at this point? Any question? Clear? Now, abhi to kya hai? If it is clear to you in the pictures, you can write down the definition very easily, right? Because now you should know what is the idea of distance in R square and the distance there. Distance there will give you what? So here I say that a most generic thing, the distance between x comma y and a comma b is less than delta, and here mod of f of x comma y minus L is less than epsilon. Right? So again a definition, right? Now this distance one can take so whenever this thing happens, we have this for every epsilon positive, right? अब थोड़ा सा मुश्किल हो गया डेल्टा एप्सिलॉन वाले क्वेश्चंस यहाँ पे, राइट? सो इसलिए मैं पूछता नहीं हूँ, राइट? सो दैट्स गुड थिंग, राइट? Any idea? So here, since there are different kind of distance defined in R square, I have taken Euclidean distance. You can also take maximum of mod of x minus a comma mod of x minus b. That's another distance. So if you remember in one of the sample paper, I have mentioned that, right? To define the definition of limit in that sense. In one of the sample paper, I have given you the distance as well, right? So this is the whole scenario. Now, once you understood the definition, I need to do two things. So if f of x comma y is given to you, and if x comma y approaches towards a comma b, either limit will exist or will not exist. So first I will take, I'll give you one, I'll show you, but I will not prove it. I leave it as an exercise for you to enjoy at the tea time, that limit of the function exists. And the second case when limit does not exist. So I will do a lot of examples of limit does not exist. Then I will do one example of limit existence. Okay. So I think that's what it is. Let us see. So this function here, see how beautiful function is, right? So you can see that there is a problem at 0 comma 0, right? So you remember sin x by x, limit x tends to 0 is what it used to be? 1. Here also it is 1, right? But how will you show it? So enjoy the beauty of this function, right? At a cup of tea you will see the beauty. Domain I have written for you, right? This limit is 1. I just gave you this example rather than, okay. I will show you how to show that limit exists in a couple of next examples before you know. So this is just, start with beauty. This is very beautiful thing, right? So let us take another one. Function is x square minus y square divided by x square plus y square. And I want to find whether limit x comma y approaches towards 0 comma 0 exists or not. Okay? So I should mention this. Limit x comma y approaches towards 0 comma 0 is what of this function? So function is, if you can, I don't know whether you are able to see this, x square minus y square divided by x square plus y square. This is your fx comma y. Now you see, showing that the limit does not exist is very easy. How? See, I have to show that the limit exists for all paths, right? Whenever x comma y approaches towards a comma b from any direction. So if I look at the function, you see, observe the beauty. If I approach x comma y towards 0 comma 0 along the line y is equal to 0, what will be the limit? 1. And if x is equal to 0, minus 1. दोनों अलग अलग है. अगर लिमिट एग्जिस्ट करेगी थ्रू ऑल पाथ इट शुड बी सेम, सो लिमिट डज नॉट एग्जिस्ट. हो गया ना? राइट? So by observing the function and finding two paths for which the limit is different, we can say that the limit does not exist, right? If it exists, it should be same along all paths. So I have to only produce two different paths for which the limit is different, right? So along line along x-axis, so when y is equal to 0, this limit basically of f of x comma 0 will be 1. This is true for every x. And along y-axis, when x is equal to 0, limit f 0 comma y is equal to minus 1 for every y. Right. So therefore limit does not exist. Right. And you can see also, right? You can see also the function behavior at origin, right? So if you draw the graph or if you plot the function, probably you can guess that the limit does not exist at that point, right? But in order to show that limit does not exist is very easy. Take two different, if you are able to find two different paths and it turns out that the limit is different, the limit does not exist. Fine. So it's easy thing. Any question at this point? सब समझ में आ रहा है? Fine. I have to show that if the limit exists from any path, whenever x comma y, the generic point approaches towards a comma b, through any direction, the limit should be the same. Okay, now you go a little bit further, take another example. This example is x into y divided by x square plus y square. Now can anyone tell me whether the limit exists? The function is x into y divided by x square plus y square. Along x equal to 0, what is the value? Huh? Along x equal to 0? 0. Along y is equal to 0? अब क्या हुआ? अब तो लग रहा है कि शायद एग्जिस्ट कर जाए, राइट? हमने दो पॉइंट देखे आसान, x एक्सिस y एक्सिस के along and turns out the limit is same. पर अभी तो ब्यूटी बाकी है, राइट? So look at this. So we say that ठीक है, along y is equal to x, along the line y is equal to x, what will happen? Y is equal to x will be what? X square divided by 2x square is equal to half. हो गया काम, right? In two cases, the limit is 0. In one case, limit is half. Limit should be same in all the three cases. So it does not exist. Right? Got the idea? First you try along x-axis, then y-axis. If they are different, limit does not exist. Okay? If they are same, try straight line like this, y is equal to x, line passing through origin, right? And इस बार अलग आ गई, so then you are done. Okay, take the next example. in this example, this is x times y square divided by x square plus y raised to power 4. See how beautiful the function looks like, right? Now, you see the earlier three tries that we do, y is equal to 0, x equal to 0, or y is equal to x. All are the special case of line y is equal to mx, right? Or a special case of y is equal to mx. So why not try y is equal to mx directly in this and see what happens? What is m? The gradient, right? So y is equal to mx, that line passing through origin, right? So let us compute the limit along the line y is equal to mx and see what happens. Again, I want to compute the limit as x and y approaches towards 0, 0. Along y is equal to mx. What will happen? F of x comma y is equal to f of x comma mx is equal to m square x divided by 1 plus m raised to power 4 into x square, right? Now this goes towards 0 as x, y approaches towards 0, right? Correct? So that means along any straight line passing through origin, this limit is 0. अब क्या लगता है? Yes? कुछ बोलना चाह रहे? हाँ? Yeah, so now change the curve and see what happens, right? Yes, show करना के limit does not exist is very easy actually. You know, just try some curve and say that if the, at two cases the limit is different, you are done, right? Show करना exist करती is a bit tricky thing. So there you will use your real beauty epsilon delta, right? Okay. So if you take the parabola along x is equal to y square, then we have f of x comma y is equal to f of y square comma y, and this turns out to be half. So does not exist, because in the previous case it turns out to be 0, and in this case it is half, so limit is different, right? If you are able to find two paths whenever x comma y approaches towards a comma b and the limit is different, mean limit does not exist, right? Fine. So I gave you some flavor of this limit. Now let us see one example.